Okay. Let's resume our discussion. So that's what we were left with. The definition of these two key parameters, x1 and x2, that for convenience can explain all the behavior of omega matter, omega phi, the equation of state parameters, the equation of state function describing our field, and the effective equation of state, together with the other Friedman equation, h dot, that is going to be convenient for our derivation later. Okay, so here we are. Then we study, given these key quantities, we studied the key features of our phase space. We have seen that there are regions where we have acceleration, regions that are unphysical, because they will give you a negative density of matter, regions in which the density of matter must be equal to 0, and now we are going to regions that are dominated by the potential, regions that are dominated by the kinetic term, where the potential is equal to 0. Okay? So all of that has been basically seen immediately just by looking at the definition of those quantities. Then, after having defined our x1 and x2, we made this change of variable. We are going to do something else, that a further way of simplifying our life. So we are going to define the system in terms of e-folding. So we are going to change, basically, we are going to change characterize the dynamic of the system in terms of e-folding, or the e-folding number n. N, which is just a definition, that's defined as the logarithm of A. And therefore, if we are going to have our derivation with respect to the scale factor A, we can link it to the one of e-folding. To do that, we use the definition of the double function, which is A dot over A, which is just the ln A over, the derivative with respect to the tau, right? That's the derivative of A with respect to time divided A itself. That's a logarithmic derivative, okay? Logarithmic derivative. Again, remember that we are using the conformal time for the dot, okay? Every time you see the dot is not the time like the c squared, t squared in the metric, but is the times A squared. The A squared is out. Remember, we use this conformal construction of the metric. And this guy, even the definition here, is the derivative of n with respect to the conformal time, the tau. So we get rid of this logarithmic derivative. Therefore, whenever you have a derivative with respect to the conformal time, that's equal to the derivative with respect to n. So all the dots that we had before, we are going to transform in derivatives with respect to n, and I'm going to use prime to distinguish it. And here we are. Now we are in the condition, we have a slightly more convenient way to address the evolution of the system as a function of the expansion function, now as a function of the scale factor, now as a function of the e-folding number. We have our our more convenient parameters. We can start to study the dynamics of our system. Therefore, we're going to jump into the Klein-Gordon equation and see what the system is going to do. Okay? And again, for convenience, we are going to transform this second order differential equation into two, so that's one second order differential equations, into two first order differential equations. Okay? which is immediately done thanks again to our parameters. Because in the Klein-Gordon equation, we would have phi dot dot, but if we express it in terms of x1, you see there is already a dot, a phi dot inside here. Therefore, x1 dot, one derivative, corresponds to a phi dot dot in this equation. Okay? So let's start to do that. We get our Klein-Gordon equation. So phi dot dot plus 3h phi dot plus v derived with respect to the field equal to 0. And we just change our dots with respect to the prime derivatives. So we get just factor of h to the power of 2, nothing more than that. So we have h to the power of 2, so we have twice because of the double derivative, phi prime prime plus 3h to the power of 2. So we have one derivative, but one h is already there, so we have the power of 2. Phi prime plus v divided with respect to phi, which is unchanged. Then we can just do like this, oops, to get our Klein-Gordon equation expressed with respect to derivatives. Therefore, our phi prime prime is equal to minus 3 phi prime minus v comma phi over h to the power of 2. And now what? We can use the definition of x1 prime, of x1, once we express phi dot with respect to phi prime, the derivative with respect to phi prime, so it would be just this expression times h. We would cancel with this one. Okay? And then we have the potential here, phi. And we can take it from the definition of x2. So we basically are going to have our phi dot is going to be equal to h phi prime. Our potential is coming from here, and we just plug them here, and here. Sorry, we take sorry, not the potential, we take the h here. Okay, we take the h from here, we plug it into here. So there was an expression with respect to x2. If we do that, we get minus 3 square root of 6 over k, so you see this factor popping up, x1 minus 3v divided with respect to the scale factor v, k square v, x2 squared. And we leave it there. Okay? Just a substitution for phi prime coming from the definition of x1, using the definition, and h coming from this h that is containing x2. So now, you see, we have phi dot dot, which is expressed with respect to x1 and x2 to the power of 2. Okay? That contains what? First order derivative of phi dot. You see, we are changing from a second derivative to first derivative. That's the trick. Then we want to see the evolution of our system, right? Our system characterized by x1 and x2. Therefore, what do we want to look at? At the evolution of x1. We want to see how this guy is changing. And the same is going to be done for x2. So we just, x1, we computed the derivative of the definition, so we just computed the derivative of x1, and we have a constant, the k over square root of 3, then we have phi dot dot h minus phi dot h dot over h to the power of 2. Well, now we can use our previous results, and look what we have here. There is an h dot divided h squared that we derived earlier. Okay, so we know what is this expression as a function of x1 and x2. And the same goes here. Therefore, what we get is k over square root of 6 of phi dot dot over h plus phi dot 3 x1 to the power of 2 plus 3 half 1 minus x1 squared minus x2 squared times 1 plus w effective. Now what we can do? Well, we have a dot and a dot here. Guess what? We are going to use this definition of derivatives. Therefore, we are transforming our dots into H derivative prime, meaning with respect to the number of e-folding. If we do that, we get an H x1 prime, right? Just change that. Equal to, we do the same here, so here we get a factor of h to the power of 2, and here we get a factor of h. Then we can pull out, and we have our constant, k square root of 6, h, and then we have our phi prime plus phi prime, and then we have 3x1 squared plus 3 half 1 minus x1 squared minus x2 squared 1 plus w 1 w effect m, yes, no, it's not effective, sorry, that's m. The effective is not popping up here, okay? 1 plus this, and then that. Tuck, and tuck. So we have the evolution of our x prime, okay? Then what we can do is to change these two guys. Okay, you see we have a phi dot dot, and what do? Oh, we know phi dot dot with respect to x1 and x2. So we plug it in. As well, we have the definition. We also know what is phi dot, so sorry, the phi prime, which is coming from here. Right? Just from the definition of x1, we transform phi dot into h times phi prime, and we can just plug our phi prime here, which is going to be a function of x1. Okay? We make this substitution, and what we get, just simple annoying algebra, minus 3x1 plus lambda x2 squared plus 3 half 1 minus wm times x1 squared plus 1 plus wm 1 minus x squared, and that's what we got. We know the derivative of x1 as a function of x1 and x2. Very, very convenient. You see? First order differential equation. This is one. Not enough to close the system, because we started with a second order differential equation. And therefore, we can do the same trick with x2. The derivation is the same, okay? We just use the definition of x2. We compute its time derivative. And then we substitute the dot-dot derivatives with respect to prime derivatives. And then we can use the Klein-Gordon equation to change this guy, and the definition again of x1 to change this guy, to have a function which is merely a function of, you see here, that's a function, x1 prime is a function of x1 and x2. Okay? So we know, once we set a location in the phase space, we know where our solution is going. Okay? Nice. So our x prime, the story is the same. I just copy it here for completeness. Same story. So we have our x2 prime. So we know also, given a location in our phase space, where the solution is going. Okay? What have we done here? Look what popped up here is a number, lambda. Well, actually it can be a function in general. And we defined lambda to be equal to minus v comma phi over kv, which is equal to minus 1 k derivative of the logarithm of v with respect to the phi. You see, this is so that's the definition. Derivative of phi, of v, of the potential respect of the value of the field, divided k v. Okay. You see, derivative of function divided by that function itself. This is a logarithm, a logarithmic derivative. What does it mean? This tells you what is the logarithmic steepness of your potential. Okay? So you see we are starting to pop up other quantities that are characterizing the potential in a very generic sense. So we don't need anymore to know what is the specific function describing V, but we just need to know how steep is your potential. Okay? Then we can continue because lambda, you see, is a function of the potential. But the potential is a function of phi, right? And if we want to stay fully general, this guy can be evolving. So what we do? We need a third equation, because we have three variables, x1, x2, so x1 prime, x2 prime, and lambda to be characterized. Therefore, we're going to do the same, and we want, as we did for x1 and x2, and we want to know how lambda is evolving. In a certain location, we want to know how lambda is changing. Therefore, we just use the definition of lambda, so it's just a matter of computing derivatives of this quantity. And you find out that this guy is equal to minus square root of 6 lambda squared gamma minus 1 x1, where we introduced a new parameter gamma. Okay? I don't do the math yet. This is just definite a derivative, nothing more than that. Okay? Where we end up identifying gamma, which is characterized as v comma phi. So that's the potential multiplied by second derivatives of the potential with respect to the of the field, divided the derivative of the potential with respect to the scalar field to the power of 2. What is this characterizing? The curvature. We have a double derivative. This tells you, gives you information about the curvature of the potential in a certain location. So with this gamma, you know how steep it is. And with this lambda, you know how steep the potential is in a certain point. And with this gamma, you know what is. Now you have information about the curvature of the potential, no matter how the potential looks like as a whole. You want just a local behavior of your potential. Here we are. These are the key ingredients. These are the key equations that are going to tell us how the system evolved. One for x1 prime, one equation for x2 prime, one for lambda prime in the full generic scenario, and a gamma and lambda that tells you what is the potential in a certain location. Okay? You change v, and you can characterize your lambda and your gamma. Or if you want, if you have a solution that have a certain gamma and lambda in a certain location of your phase space, you can look at whatever thousands of potentials you can assume that fit those values. Then you know that your system is going to evolve in that way. Okay? You don't need to compute everything from scratch every time. Nice. So here we are. We have x1 prime. Again, that's a function of x1 and x2, gamma, and all of this here. So I can cancel this board. Okay. So x2 prime equal to another function x1 of x2, and then we have lambda prime, which again, g, L of x1 and x2 as well, we have gamma, okay? So that's the set of equations that we need to solve in general to find the evolution of our system. Yes? Gamma prime, no, I mean, is not important. We are going to see that the key, well, is going to be important, but I have to make simplifications. For example, when we're going to look for tracker solutions, you see what that is. I'm going to assume the gamma is nearly constant. Okay? Then we are going to just see for a given gamma what do we have. Okay, I'm not going to track it. These three are going to characterize your system. Okay? Then gamma is just coming out from your potential once you specify it. Okay?
When is gamma prime?
Sorry?
When do we need to include gamma prime? I mean, we make simplifications.
I mean, you will see that, for example, we are even going to use lambda equal to constant at the beginning, okay? And that's characteristic of a very specific potential. If we have an exponential potential, then gamma is constant and lambda is constant. And the idea is that if you assume that the lambda and gamma are not, or are evolving slowly in time with respect to h, okay, h gives you the rate of expansion of the universe, but if the rate of change of lambda with respect to that is smaller, then you can assume for each time frame a constant lambda and a constant gamma. Okay? This gives you a picture of the evolution of the system. After doing that, I'm going to use lambda prime as a function, so non-zero. Okay? And then we will see also how we can change from how the critical points are going to mutate, okay? From one nature to another as lambda is changing. Okay? Gamma is a secondary order importance. We're going to see that for the tracking solution. That's, but we are going to arrive there. Okay? Good. So, nice. That's what we have. We have our phase space, which is telling us a lot of stuff. Here it is. We have our set of equations that need, in principle, to be solved numerically. We cannot do that. So what we are going to do now is to find very special solutions. So we are at step 4, which is the one where we identify the critical points. Okay? Critical points are the points where these derivatives are not changing. For x prime 1 equal to 0, and as well x2 prime equal to 0. So these are minima, maxima, or saddle points that give us characterization, further characterization of the phase space. So we are going to identify very special position here. And keep in mind that these are solutions. So they look like points in your phase space, but these are full solutions. Your solutions where if your system is, for example, in a stable point here, we know that it will remain there. But if you have a time frame, it's like looking, okay, I'm not moving, but time is flowing. I am a solution, okay? So these are trajectories that correspond to points. They just happen to be points. Good. With that, now what we want to do is to study the stability of those points. And in doing that, that's something that is done in hydrodynamics. If we want to see if a system starts to involve instabilities and this sort of stuff, we are going to use a perturbative approach. Okay? that will help us to linearize our set of equations, our system of equations. Okay, that's the usual perturbative approach. So what we do, we are going to characterize x1 in the surroundings of one of those critical points. So it's going to be x1 given a critical point, so here, plus a tiny deviation around the critical point. Okay, so if this is xc, we are going to look how the system is evolving in the surroundings of this point, very close to it. So it's not a derivative. All of this together means a little shift, a very small shift with respect to the critical point. Same goes for x2. x2 is equal to x2 critical point plus a tiny deviation with respect to the location of the critical point. Again, just to be clear, x1 critical point, delta x in general e, so one or the other, must be much smaller than 1. So very small with respect to, so very small deviations from the critical point. So that's our x1, x2 critical. We are looking for the behavior of the solutions in the surrounding. Okay? So what we do then, we have defined, we have split x1 into these two terms. We just plug them in into our equations. Into here, 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 here. Plug them means that we have the function describing, let's call it f1 now. I mean, changing names, but it doesn't matter. Understand what I'm talking about. So that's the function, you know, all the complicated stuff that I wrote before, defining the derivative of x1. We plug in our perturbed value around a critical point into here. And we are going to get, we are going to collect all zeroth order terms. So all terms that do not depend on the derivative of phi here. So it is going to be our solution, our derivative at the location of the critical point, plus all the terms that are coming from first order terms. Therefore, everything that depends on this delta x1, not products or second order terms. Okay, so we are going to have a function that I call df, that's for the critical point 1, and which is a function of the deviation with respect to the critical point. So only first order term. So that the zeroth order term, zeroth order, this is first order. Then there will be higher orders, okay? For example, products of this tiny deviation, but is a small thing to the power of 2, which is negligible with respect to the other one. We stay at first order. That's why there is this approximation here, okay? And the same we do for x2. Once in doing that, our perturbative approach, as usual, is going to give us a linear, a first order differential equation, okay? Therefore, we're going to have d over the n of d x1 prime, d x2 prime, and then we have a matrix, d x1 and d x2. Okay, a linear expression, a linear equation, that's it. Where is it gone, this guy here? Well, that's equal to 0. Why? Because we are looking for the surroundings, for the critical points that satisfy this condition. Okay, for this guy, our function that describes the derivatives of the solution in the critical point are equal to 0 by construction. We are left only with the evolution of the perturbed values, of the small values in the surrounding of this point, which is linear. Okay, and A is just, again, as a function of x1 and x2, and is just a matrix A, B, C, and D. Okay, so A belongs to the space of matrices of real number of matrices 2 by 2. Then whenever you have a matrix and a system which is described by a linear equation, what is always convenient to do is to find the eigenvalues. Therefore, we diagonalize our matrix to capture all the relevant information describing the solution. For step E, we linearize our system to get that with the perturbative approach. God, it's very fully apart today. B, we look for the eigenvalues. So we diagonalize. Diagonalize A, and we find eigenvalues. Mu. They are going to be 2, of course. So in doing that, I'm not going to tell you how to diagonalize a matrix because that's linear algebra, and you know. But bottom line is that you need to basically rotate your system, your axis, if we want to say so, such that we have a new solution, the x2, which is a linear combination of the other two. This is just a rotation and a rescaling. Okay, that's what you do when you A, B, C, and D, take x2, when you apply your diagonalization. And therefore you get your equation, which is much simpler, because you split the terms such that the y1 and the y2 are going to be described by a diagonal matrix now. Okay, now I just sketch it. What you do, you just solve this expression. Okay, you have your the y prime, with derivative with respect to n, is equal to mu1 multiplied the x1. And you can find the solution of this system. Therefore, the y prime over the y is equal to mu. Let's say that this is one of the two eigenvalues, okay? So what I did is just to get this expression, and it's just that. I just brought this guy on the other side. So we have the derivative of this guy divided this one. And what we're left with is the eigenvalue, okay? You do for this line and for the other line. You can solve it. You see that's very simple. You get an exponential as a solution. For your exponential, your solution is going to be dy e equal to some coefficient. So let's give you the normalization that is set by the initial conditions, mu e, and then you have a okay, so remember that this guy is the y over the n. So, speaking with the terminology of physics, you get this the n and you bring it on the other side. When you integrate this term, you get a mu e n. Here you get the solution is the logarithm of y. You compute the exponential to have the y prime on this side, the y e on this side, and the normalization e on this side with the exponential. Okay, just solve this equation. I mean, that's trivial. Okay, nice. Now, just to complete the picture, the eigenvalue that gives you your solution are 1/2, and then we have minus 1 e plus e to 2, so this will be a, b, c, d, d plus minus square root of d, where d is just knowing value, so that's a plus abd, yeah, the power of 2 for a, yeah, a d minus b c, and then c d. That's what we get. Okay, that's what we have. So we have our solution here in this rotated frame. So we are not using finding a solution with respect to x1 and x2, but the solution in some weird coordinate. So we are going to have y1 and y2, which is a little bit annoying. Okay, so what we do, we rotate back. We rotate back to go from this y. Once we know this y, we go back to the typical x1 and x2. And we know that need to apply an expression of this sort. So it's going to be the inverse of the transformation, where we're going to have the delta x1 is going to be the linear combination of this delta of y. Okay? For the solution, we go back to x1, x2, linear combination of the two, and we get xe, so that's x1 and x2, that's the same structure. I sketch it. Alpha e coefficient 1, e to the mu 1 times n, plus alpha e coefficient 2, e mu 2 n. That's your solution. And now we can get immediate consequences out of this expression, just by looking at the values, at what the eigenvalues are, if they're positive, 0, or negative. Okay? Let's focus on one of these guys, for example, this one. This term is an exponential, right? So we have e to the power of minus, in this case, 2, let me write e because it can be one or the other, times n. But this eigenvalue can also be complex. If we look at this expression, giving you your two eigenvalues with the plus and minus, if delta is smaller than 0, you get a complex term. So it can also be complex. What's the consequence here? Let's give a look at that. So let's start with something simple. Let's take mu, and therefore we can split it, okay? So we can split this guy into a real and a complex number. So let's call, I don't know, let me use a plus b n, okay? A and b are not the one of the matrix, are just two numbers, okay? Are just two real numbers, a and b belonging to R. Just to say that, just to split the two components of real and complex component of the number, okay? Whatever are these values, doesn't matter. And therefore, if I have this plus, I have en, oh, there is an e missing, okay, that's the complex component, times e to the e b n. Look at this. What happens if a is positive? As n is growing, as the time is growing, okay, the exponential is going to blow up. So if a is larger than 0, the function will exponentially explode. That's a sign of instability, because we are in the surrounding of these critical points. We are on our phase space somewhere here, and we are in this vicinity, and if this is the case, the deviation is exponentially growing. We are, boom, jumping away from it. Unstable point. What happens if a is smaller than 0? Then it's the opposite. We have e to a negative numbers to n, and therefore we have a damped we have an exponential decrease of the value of the deviation from the critical point. Therefore, if this is the critical point, and we are in its vicinity, we are sucked in, and it goes to 0. We stay there. This is a stable point. That's about this part of the number. What happened to this guy? Well, E, B, N, exponential of this guy. What's that? We can write it in terms of cosine and sinus. That's a circle. Okay? As N evolves, this is a circle. Scaled by this value. Okay? Therefore, if B is different than 0, then we can have a solution with A positive that goes like that. With this guy is sucked in this way. Okay? If B is like that, we just fall on it. Or we are repelled by it. Okay? So you see we have different kind of stability points that are coming out of this derivation. Stability or instability points. So what you have? If D is larger than 0, then it means that, for example, and if you have mu1 larger than 0 and mu2 larger than 0, then the point is unstable. Unstable. Both are positive, and no matter what is the direction, we are coming out. We're going away from it. Okay? If the way around mu1 is smaller than 0 and mu2 is, let's take it again, smaller than 0, then this is a stable point. Stable. These are two real numbers. This is like that. And we get this negative. The solution goes to the critical point. So in this case, we have our critical point, and this is what's happening. And in this case, no, sorry, negative, so this is happening. In this case, it's unstable. That's what is going to happen. And these eigenvalues are associated. These eigenvalues. So our eigenvalues are related to the eigenvectors. So if you have an eigenvector with this eigenvalue pointing in this direction, mu tells you what is the speed at which you go away along that direction. Okay. You have the other eigenvalue pointing in this other direction, and the other eigenvector, an eigenvector pointing in this direction, and the eigenvalue associated to it tells you what is the speed that you go in that direction. And then, of course, you have the in-between situations. Okay? So you know that, for example, you have something like that. Okay? Very fast and a little bit, but still an unstable point. Then you could have, for example, mu1 smaller than 0. So we have an instability here, but mu2 can be larger than 0. That's a saddle point. Well, we would have something like that. Okay, so we're going to have, for example, I said this one is negative. Therefore, we are going to have for the x1 for this eigenvalue, we have like a stable situation, and an unstable situation for the other one. That's a saddle point. It means that if I start from some initial condition here in the vicinity, my solution is going to do something like that. I'm attracted once I'm here, whoop, I tend to be repelled by the other side. Okay? Then what happens if instead D is smaller than 0, this guy is negative, therefore B is going to be different than 0. And we have this circling behavior, which is scaled by this value. Therefore, we could have unstable spirals or stable spirals. Okay, again, point that can be stable, if that's what we have. Stable spiral or unstable spiral, if that's what's going to happen. Okay, that's if the mu e value are smaller than 0, stable, and that's if the mu e value are larger than 0. Okay, let me do the last drawing so that I complete the full picture. We go back to our phase space. We have our x1, we have our x2, we have the regime of allowed, physically allowed solutions. We might have mathematical solutions that go out of it. If you go out of it in some physical regime, then you can throw away your theory. It's one of the criteria to say the theory that I built up is not valid. Okay, I throw it away. So that's our regime, 1, 1, and 1. And for example, we have an unstable point here. So this one has mu1 larger than 0, as well as mu2 larger than 0, unstable. Okay? Then let's say that we have, I don't know, a saddle point here. So we are going to have, for example, mu1 smaller than 0. So you know that this is coming from like this. Mu2 larger than 0. You know that we are going to have something like that. It's a saddle point. Okay? Saddle. And then let's say that we have a stable point. So in this case, we are going to have stability. Whoops, too long. Stable point for mu1 and mu2 are both smaller than 0. What are going to be our solution? Look, we have these critical points. In all the other regime, we know that the derivative of x1 and x2 are different than 0. Therefore, we know that the solution must be moving around in between those points. But we know that if here I'm forced to go away, I have to go either here, be attracted, and then being repelled, to be sucked in by this other point. Our solution is going to look like that. If I have this other value, then I know that I'm not escaping because I'm my physical area that is constrained by the continuity equation for matter, and I'm going to have something like that. Okay? That's an example of what you can get right away by these very simple considerations. You have solutions that are confined, and you know where they are going. Okay? You don't know, you don't have anything that looks like that. From here going this direction, there is not. So you're going to have a phase space that will look like that. Okay? This is just a sketch. I put there 3 critical points. Then we are going to do consideration more physical and look for critical points that you get with an actual cosmology. Okay, and we will see how this is, how everything is going to evolve. Now, not only stable points are important, but also saddle points are important, because what we want in the end for our cosmology to have a system that starts from a radiation epoch, goes to a matter epoch, and then goes to an accelerated epoch, so a field dominated. And we want this guy not to be a a stable point at all times. Because if this happens, we would start, for example, with radiation. We stay here and we remain there. We don't arrive nowadays. Our cosmology is false because this is an observation that must be respected. Therefore, this guy can be or a stable point, but then lambda is changing, is evolving as a function of time, and therefore it becomes a saddle point, and we are free to move toward another stable or other saddle point. What we want to be our dark energy regime? A stable or a saddle point? Could be either. It could be also a saddle point. We don't need it to be a stable point, but we don't know. You know, we don't know if after this phase of field-dominated epoch, we are going to then transition to another epoch. We don't know. That's in the future. There are no constraints. Could be a saddle point. But it's, let's say, more reassuring to think that this guy is a stable point because it would be the natural evolution of the system. We know that we are starting somewhere, and then no matter what we do, in the end, we arrive. I mean, we might be falling in another stable point, but if we are transitioning to a matter-dominated regions, we are sure that we are going to fall into a field-dominated region. So it's more likely, if you wish, okay? But it could be either, because we don't know what's going to happen in the future. We don't have observations for that, okay? Good. So, bottom line of this discussion, we use the Klein-Gordon equation. We move from a description of the phase space with respect to phi and phi dot in terms of two more convenient variables, x1 and x2. We introduced we moved from the derivatives with respect to time, to tau, to derivatives with respect to the number of foldings, okay? And we transform, using these two tricks, we transform one-order differential equations in two first-order differential equations, where we have as well characterized the potential as a function of lambda and as a function of gamma, okay? Where this guy characterizes the steepness, the exponential steepness of the profile, and this guy, what is the curvature given a certain phi, okay? So characterize the potential in a very generic sense, no matter what is the specific shape of the potential. Then this guy could be constant, so it is evolving, it's a function of n, that's our new time variable, right? Could be evolving, therefore phi dot could be different than 0, and that's given by a very specific potential we are going to study during the next lecture, but in general can be evolving, okay? So there is how the potential is going to behave, so the shape of the potential, if you wish, in that certain location of the phase space is going to change, okay? And therefore this gives rise to different features. So in the next lectures, we are going to look at this scenario, lambda equal to constant, and we are going to derive critical points that we would expect to find in a cosmological model, okay? After having done that, I will see if I have the time to consider the case in which this is evolving as a function of time, okay? And then we will see what changes in one scenario with respect to another. And after doing that, at the end, you see that now we just have a cosmology where we used omega m, where we used omega phi. There are only these two species. What we are going to do next is going to use matter, in terms of baryons and dark matter, radiation, as well as the field phi. Okay, so we are going to have a three-dimensional phase space, and then once have to live in this three-dimensional phase space and see if the cosmology is moving from the three epochs that we know exist. Okay, good. We can stop here. Thank you very much. I'll see you next week.